Before we go beneath the ice, this is Europa, one of Jupiter's 4 large Galilean moons, orbiting deep in the outer solar system. It is a small world wrapped in a bright, fractured shell of ice, and scientists believe a global ocean is hidden underneath. The safest place on Europa may lie beneath its ice, yet reaching that shelter could kill you long before any ocean comes into view. Picture landing under Jupiter's glow, drilling downward for years, and finding that your new home doubles as the ceiling of a moving alien sea. Radiation would tear across the surface above you while black water waited under crushing pressure far below, cut off from every ray of sunlight. Every breath, calorie, and degree of warmth would trace back to a machine forbidden from failing, because nothing else down here would keep you alive. Europa looks like a frozen refuge from a distance, yet it may rank among the hardest places in the solar system to keep a person breathing. Strangely, the same ice standing between you and the ocean could also become the shield that saves you, which turns this into a question about engineering rather than geography. Could we actually seal a working copy of Earth inside a moon that was never built to hold one? Slightly smaller than our own moon, Europa hides a global saltwater ocean beneath its bright crust, one that may hold roughly twice the water in every ocean on Earth combined. A rocky seafloor likely sits beneath that ocean, and the chemical reactions happening there could supply enough energy to support life, at least in theory. That single possibility has turned Europa into one of the most closely watched worlds in the entire search for life beyond Earth. Water is the first thing that makes Europa feel almost welcoming. You'd need it for drinking, hygiene, farming, cooling, radiation shielding, and breathable oxygen, and here it surrounds you on every side. Having it nearby, though, is nowhere near the same as being able to use it. Antarctica is buried in ice too, and nobody pretends its interior is easy to reach. Europa takes that same problem and stretches it across tens of kilometers of frozen crust instead of a few. In December 2025, Juno project scientist Steve Levin and his team at NASA's Jet Propulsion Laboratory published new measurements, gathered during the spacecraft's 2022 flyby, showing that Europa's cold, rigid ice layer averages about 29 kilometers thick in the region they studied. The full shell could run even deeper if a warmer, slowly moving layer of ice exists underneath that rigid crust, as some models suggest. Reaching the ocean, in other words, might mean drilling through a frozen barrier deeper than Mount Everest stands tall. Long before any drilling starts, a crew has to survive the trip itself. Europa Clipper, NASA's robotic scout, launched in October 2024 and won't reach Jupiter until April 2030, and that's without a single person on board. A crewed mission would haul far more mass, thicker shielding, redundant life support, spare parts, years of food, and some plan for getting home again. Once you're out there, no ambulance is coming and no doctor on Earth can take the wheel during an emergency. Radio signals need tens of minutes just to cross the gap between you and home, so by the time Mission Control hears that something broke, you've likely already fixed it, or you haven't. Arrival, in short, brings no relief at all. Jupiter wraps itself in a vast magnetic field packed with high-energy particles, and Europa drifts through that field like a target inside a running particle accelerator. The bombardment is so constant that even robotic spacecraft need hardened electronics and heavy shielding just to survive a flyby, let alone a landing. NASA built Europa Clipper to dart past the moon in brief passes rather than linger nearby, partly just to limit how much radiation it soaks up. Human tissue doesn't come with a replacement circuit board, so any surface habitat would need thick shielding running from the moment the crew steps out. Water, polyethylene, regolith, and packed ice could all help soak up that radiation, which points to one obvious fix: bury the base. Even a fairly shallow layer of ice above your head could cut the worst of the particle exposure dramatically. That turns Europa's frozen crust from an obstacle into something closer to the wall of a bunker built by the moon itself. Ideally, the crew wouldn't land on empty ice at all. Robots sent years ahead of them would already have carved a shaft, melted out chambers, run the power cables, and pressure tested every seal. Those same robots would also have to map the cracks hiding beneath the surface, because Europa's ice is anything but a still, uniform slab. Jupiter's gravity squeezes and releases Europa over and over as the moon follows its slightly elliptical orbit, a process called tidal flexing that generates heat and drives the fractures, ridges, and broken terrain scarring the surface. That same flexing may be what keeps the ocean liquid under all that cold crust in the first place. A tunnel cut into ice this active wouldn't just sit there. Pressure could slowly seal it shut, a shifting fracture could snap a cable, and equipment running warm could melt the walls faster than anyone planned. Shut that same equipment down though, and the chamber would start freezing in around it instead. On Earth, a building stands because the ground under it holds still. On Europa, that ground behaves more like an extremely slow glacier under constant gravitational stress. Engineers would have to design a habitat that can flex, shift, and repair itself on the fly, since rigid walls would simply crack under the changing load. Flexible joints could absorb that motion instead, but every joint you add is also one more place a leak can start. And a leak on Europa wouldn't feel like a gentle draft. The moon's oxygen atmosphere is so thin it counts as a vacuum for human purposes, holding only a sliver of Earth's pressure despite genuinely containing oxygen molecules. Step outside without a pressure suit, and body fluids exposed to that near vacuum could begin boiling even at normal body temperature. Consciousness would fade within seconds as oxygen left your blood, all while surface temperatures sat near minus 170 degrees Celsius. Cold enough to kill you, though contrary to what movies suggest, not cold enough to freeze you solid on the spot. A suit built to survive all of that would really be a personal spacecraft rather than winter gear, with every glove joint, battery, valve, and seal carrying your life on its back. Low gravity would make some things easier. Europa's surface gravity sits at only about 1/7 of Earth's, so heavy tools would weigh far less, and you could jump much higher than you're used to. Mass doesn't vanish just because weight drops, though, and even a large drill that feels light in your hands could still crush you if it started moving. Weak gravity would also run a biological experiment nobody has ever tried. We know microgravity weakens bone, muscle, circulation, and balance, but nobody knows whether Europa's gravity offers enough pull to slow that decline over years of settlement. Rotating living quarters could generate artificial gravity, but building a rotating structure inside a pressurized ice chamber adds a whole new layer of mechanical headache. The first base might just accept gradual physical decline instead and simply limit how long each crew stays. That leaves an uncomfortable truth sitting at the center of the whole project. A place can be technically survivable without ever being healthy enough for permanent human life. Power would decide whether Europa becomes a working laboratory or a grave, and the numbers start out against you. Sunlight this far from the sun runs about 25 times weaker than it does on Earth. Solar panels can still function out there, as Europa Clipper itself proves, but a buried settlement would need steady power through darkness, dust, damage, and emergencies that could drag on for years. Nuclear reactors would probably end up as the main and most reliable power source, warming the habitat, melting water, running industry, and driving the drilling system all at once. That same heat, though, would need extremely careful control, since waste heat can't just vanish once the outside world is this cold. It would have to move out through radiators or into the surrounding ice without ever destabilizing the base. Too little heat freezes pipes and machinery. Too much creates hidden meltwater pools that weaken ceilings and shift the stress around the habitat. Temperature, in effect, becomes architecture, with the shape of every room depending on how heat actually moves through the ice around it. A working base might end up looking like a cluster of warm capsules suspended inside one much larger frozen cavity, with empty gaps around them absorbing any movement in the shell. Water could even be deliberately frozen into new structural layers wherever engineers wanted stronger walls, so instead of fighting the ice, the settlement would essentially grow by reshaping it. Oxygen would come mainly from splitting water with electricity. Electrolysis yields breathable oxygen plus hydrogen that could be stored, burned as fuel, or fed straight into other chemical processes. Producing the gas itself turns out to be the easy part. Keeping a complete atmosphere stable is the real challenge, with carbon dioxide needing constant removal and humidity held inside a narrow range. Trace contaminants from plastics, machinery, cooking, and human bodies would slowly build up in the air, the same way they would on Earth, except Earth's forests, oceans, soil, and weather quietly process all of that for us without anyone noticing. Europa's habitat wouldn't offer any of those invisible services, so every one of those natural cycles would need its own mechanical substitute running instead. Water from your breath, sweat, washing, and urine would get pulled back out of the air and recycled again and again, and even human waste could eventually become fertilizer, but only after careful treatment. Filters would clog eventually, catalysts would degrade, and microbes would start growing in places the designers never intended. Survival, in the end, would rest less on one heroic piece of machinery and more on thousands of ordinary components staying repairable for years on end. Food would pose an even bigger problem, since hauling years of meals from Earth would eat up an enormous amount of launch mass. Any settlement meant to last would need plants, algae, fungi, or some form of cultured food system instead, and every crop would demand light, nutrients, carbon dioxide, steady temperatures, and protection from disease. Electric lamps would stand in for the sun, which means every tomato or grain of wheat grown down there would essentially be a nuclear-powered product. A single failed harvest couldn't just be shrugged off and covered by next season either, since resupply might be years away and stored food only buys so much time against repeated ecological failure. Tiny greenhouses can spiral into collapse far faster than a planet-sized ecosystem ever could. One aggressive fungus could tear through the entire food supply, and insects stowed away from Earth could find no natural predator waiting for it, and helpful soil microbes could mutate or behave unpredictably under low gravity and constant radiation. The crew wouldn't just be growing food. In other words, they'd be managing a miniature biosphere whose collapse could starve everyone living inside it. Then comes the task the entire mission really hinges on. Somehow, the settlement has to reach that ocean. Conventional drills wear down, jam, and need constant replacement parts, so Europa-specific machines called cryobots would likely melt their way downward instead, trailing a cable that carries power and communications back up to the surface. Meltwater behind the descending probe could refreeze almost immediately, which sounds helpful until that same ice ends up trapping the machine or cutting its cable entirely. Salts, cracks, rocks, and hidden pockets of liquid could all change the melting rate without warning. Hit a void, and the probe might fall, hit a dirty layer, and it might absorb extra heat it wasn't built to handle. Moving ice could also bend the tether until it finally snapped, and 30 kilometers of cable is already a massive, fragile machine in its own right before any of that even happens. Wireless signals wouldn't easily cross that much fractured, conductive ice either, so relays would probably have to be left behind at intervals during the descent, each one needing to survive years of pressure, cold, and constant movement. Even reaching the bottom of the shell would introduce a fresh danger, since ice overhead would be pressing down with the force of hundreds of Earth atmospheres by that point. Any probe entering the ocean would have to equalize that pressure carefully before opening a passage, or water could surge straight up the shaft and destroy the equipment behind it. Humanity's first glimpse of the European ocean might arrive through a camera no bigger than your hand, its lights reaching only a few meters into water that could stretch deeper than most seas on Earth. That water might turn out clear, cloudy, salty, acidic, chemically rich, or surprisingly short on usable energy. Nobody yet knows enough to promise it's safe to touch. Salt water isn't automatically drinking water, and any purification system would need to strip out salts, metals, oxidants, and whatever unknown biological material might be drifting in it. Contact with alien life, assuming any exists down there, would raise a problem far bigger than ordinary contamination control. Earth's own microbes could invade an ecosystem that spent billions of years evolving in isolation, while native European organisms might carry chemistry our immune systems have never met before. They might turn out harmless simply because they can't use our biology at all, or they might release something toxic without ever causing an infection. Honestly, nobody knows which. Planetary protection rules would end up shaping every tunnel, sampler, suit, and waistline on the base, since a human crew is basically a walking cloud of bacteria that can't be sterilized without killing the humans wearing it. Landing people this close to a potentially inhabited ocean risks contaminating the very evidence they traveled all this way to study. That buries a moral conflict right inside the engineering problem. The first humans on Europa might be fully capable of reaching the ocean and still forbidden from ever setting foot in it. Robotic probes would likely go first instead, drawing water samples without exposing the habitat directly, everything sealed inside isolated labs behind airlocks that keep the science apart from the living quarters. Waste from that lab might have to be stored permanently rather than ever released back into the environment around it. Discovery, in this scenario, would make survival harder rather than easier. Finding life would instantly turn Europa from a resource into a protected world instead. Suppose, though, that the ocean turns out sterile and chemically manageable. Could people actually live inside it? A free-floating underwater settlement sounds safer than a surface base in some ways, since kilometers of ice overhead would block Jupiter's radiation entirely. The ocean itself would work as a nearly unlimited heat sink, and weak gravity would let buoyancy support genuinely large structures. Water down there could also supply oxygen, hydrogen, and raw material for industry, and all of those advantages are real. Even so, the ocean would remain one of the most dangerous construction sites imaginable, wrapped in complete darkness while external pressure attacks every window, hatch, and structural flaw. Communication with the surface would still depend on that same long, fragile path back up through the ice, and navigation would be brutal without satellites, stars, landmarks, or any mapped seafloor to go by. A vehicle that lost power down there could simply drift off into darkness with no natural way back to the surface, and rescue crews might have no idea where to even start searching. Repairs outside the habitat would need pressure vehicles rather than ordinary diving gear, since depth alone could push external pressure past 1,000 times what you'd feel at sea level on Earth. An ocean habitat would also sit cut off from the nuclear reactors and antennas that are easiest to place near the surface, leaving long power cables as fragile lifelines threading through moving ice and dark water. For the first settlers, then, living directly in the ocean might solve fewer problems than it creates. The smarter location might actually be inside the ice itself. A base sitting several meters or a few tens of meters below the surface could gain strong radiation protection without ever drilling all the way down to the ocean. Deeper scientific shafts could stay entirely separate from the main settlement, with astronauts living in sealed chambers surrounded by frozen water rather than inside the alien sea itself. That same ice would double as shielding, construction material, thermal buffer, and emergency water supply, while short tunnels kept surface antennas and landing pads within easy reach, and nuclear systems stayed isolated in distant chambers of their own. Damaged sections could simply be sealed by freezing water straight into the cracks, and the whole base could expand slowly as robots melt out new rooms and reinforce them over time. In a design like this, the ocean becomes a research destination rather than the crew's actual home. And that's the twist sitting at the center of Europa. Its enormous ocean is exactly what makes the moon scientifically irresistible, yet the safest human settlement might never touch that ocean at all. You'd survive under Europa's ice for one simple reason: the ice protects you from Europa itself. Even then, the whole settlement would stay completely dependent on technology, where a single reactor shutdown could kill heat, light, oxygen production, farming, and water circulation all at the same moment. One broken supply chain could turn an ordinary spare part into something more valuable than gold, and a medical emergency might have to be handled with whatever equipment and knowledge already happened to be on site. Isolation would reshape the crew psychologically just as much as physically. Jupiter would dominate the sky outside, yet most settlers might rarely even glimpse it from their buried rooms. Morning wouldn't arrive with a blue sky, and there'd be no wind, rain, birdsong, or living forest waiting beyond the walls. Just a calendar humans invented, projected onto endless mechanical light. Privacy would run thin, since every person there is effectively part of the survival system itself, and conflict could threaten maintenance, discipline, and trust just as easily as any mechanical failure. A settlement engineered to survive the raw physics of Europa could still fail for entirely human reasons instead. Success out there would demand crews able to repair machines, grow food, practice medicine, run science, and simply live together under permanent pressure. Europa wouldn't reward individual heroics nearly as much as it rewards patient, ongoing cooperation. NASA's Europa Clipper is already on its way toward Jupiter right now, built to study whether the environments hiding beneath that surface could actually support life. It's set to arrive in 2030 and make 49 close flybys rather than land, gathering data that should reveal far more about the shell, the ocean, the chemistry, and the places where material moves between them. None of that will prove humans can settle Europa. It will only tell us whether the moon is worth risking far more ambitious missions on. Robotic landers would probably come next, with cryobots needing to prove they can cross the ice without losing power or contact, and autonomous submarines needing to navigate under that ceiling with zero real-time guidance from Earth. Closed-loop habitats would need to run for years without any outside rescue. Nuclear systems would need multiple independent backups, and planetary protection rules would need to firmly separate exploration from contamination. None of these challenges clearly breaks any law of physics. Together, though, they add up to a project bigger than anything humanity has ever built away from Earth. Mars, by comparison, offers real sunlight, solid ground you can just walk on, a thin atmosphere, and communication delays measured in minutes rather than hours. Europa offers weaker sunlight, almost no atmosphere at all, brutal radiation, a distant hidden ocean, and a multi-year road just to get back home. Calling this a colony would honestly hide the truth of what it really is: a life support machine buried inside an active, restless moon. Surviving there for days or months could well become possible with enough preparation, once robotic systems have already built and tested a protected base, but keeping a small crew alive for years would be a much harder problem. That might still be possible with nuclear power, deep redundancy, reliable food production, and simply no major failures along the way. Building a genuinely self-sustaining civilization down there, though, is an entirely different question, and nothing we currently possess comes close to answering it. Europa may hold an ocean larger than all of ours combined, and yet every human living there would still depend on nothing more than a few sealed rooms. That contradiction is exactly what makes the moon so compelling. Beneath the ice may sit one of the solar system's most promising habitats for alien life, while for us, that same place would only become survivable once we'd hauled almost every part of Earth down there with us. Ice would end up doing the job of a shield. Reactors would substitute for sunlight, and machines would quietly handle everything that weather, soil, rivers, and air normally do for free back home. While cooperation, since no rescue ship exists out here, would be the one resource nobody could ever resupply. If even a single layer of that system failed, the ocean beneath your feet wouldn't save you. It would simply stay there in the dark while the last warm chamber slowly froze around you. So yes, people might one day survive beneath Europa's ice, but not by becoming part of that environment. We'd survive by building a fragile piece of Earth inside it instead, with the walls separating that artificial world from death being the very ice we once thought was only standing in our way.